Sorry, everyone, for the technical problems and for the delay, but I think we are ready to get started. So thanks for coming and thanks for joining online. Thanks for your patience. This is the FI Machine Learning Coffee Seminar. And today we have Ayush Bharti from Ayush Bharti talking about his recent work on simulation-based inference. So thanks so much for coming in, please.
All right. So, I do have a few slides prepared, but I would like to take it slow and, let's see how far we get there rather than trying to finish everything. I hope, so the owl should be working and everybody should, at least online, should be able to hear me, I'm assuming. So I'm going to continue. Oh, wait, there is a... All right, good. Everybody can hear. So I'll take a slight detour and talk about something called radio channel models. I'm sure, just bear with me and it'll make sense in like 5 minutes or so. So let's say you have some transmitter here, and then you're transmitting some signal, like it could be just Wi-Fi signal that we have or some cellular signal. And then YT is the signal that is received at the receiver. And everything else in the environment is basically what is termed the radio channel, which is the radio environment in which the communication is taking place. And so when you send a signal, it's an electromagnetic signal, it can go in multiple directions. It can, there can be one path which goes straight from the transmitter to the receiver, which is called the line of sight path. That's going to arrive the fastest because it takes the least amount of distance. There could also be some reflections off of the walls or multiple reflections from tables, chairs, whatever, roof of the room, and then arrive at the receiver. So what's happening is that at the receiver, what you get is a superposition of the transmitted signal x of t, which is kind of delayed because they each take a different path. So that means the distance that they cover is slightly different. So you kind of get slightly shifted versions of the same signal, and also with different amplitude, because the more interactions that they have with objects, the more signal that they lose. And so at the end, YT, so the Y of t is basically like a sum of different versions of X of t, which are kind of with different amplitudes and different delays, is what we call. And so communication engineers, what they're interested in is to try to model how this radio channel, which is the environment, affects your signal. Because if we can do that, then at the receiver end, we can design a communication system which can then recover the original X of t which you sent, because that is the game that we're trying to play here. So if I know how the environment modifies the signal, I can kind of have a demodifier at the end to recover back the signal. And so this is usually done by modeling the environment as a filter, a linear filter, which is denoted as h of t. And that is what people try to model. And the better model you have, the better your communication system will be. All right. And so as I was saying, so your y of t is basically a convolution of the linear filter h and your transmitted signal x. And then you also have some noise, which is w. That's some additive complex white Gaussian noise. And this can be of the form, this sum of all these different signals that have arrived at the receiver. They all have their own time at which they arrive, which is tau L, and then their own amplitude, which is beta L. And then you have some, as I said, the additive white Gaussian noise. All right. One example of such a model is if you can say that these taus, which is your delays, are modeled as a Poisson point process with some arrival rate lambda. And then you say that the amplitude of the signals depends upon these times, because the fastest one arriving will have the most amplitude, and then the amplitude kind of goes down as exponentially with some rate, which is gamma. And then Q is like, let's say, the power of the first arriving component. All right. And zero mean, complex Gaussian. And so the parameters of this model would be your lambda, your Q, your gamma, and then the noise variance, which is sigma square, W. And one example of, let's say, data from this model is what I've shown here in red. As you can see, it starts off around, let's say, -80. So this is, we are looking at the power in the signal. And so that would be kind of what Q is. And then your gamma tells you how quickly the signal dies down. Sigma square W is, the noise floor, which is after the signal has gone down, what is the kind of noise that we see. And the arrival rate lambda is basically how many points per second arrive, which is how many signals the frequency of signals that arrive at the receiver. So in a small room, you can imagine that your lambda would be higher, or you would want a higher lambda because, there's a lot of interactions that take place in an open space. There might not be that many reflectors, so to speak. And so this the decay rate might be higher. That makes sense? All right. So now, in order to use this model, you need to first go out in the world and collect some data, and then you want to fit this model to those data. And let's say you went and collected some data set x1 to xn, which can be denoted by some empirical distribution q of n. And then now this model, or any model, statistical model, can be thought of as a family of distributions, p of theta, parameterized by theta. And the task that we have is to estimate those parameters that we just talked about, given some data set. And now any generative model can also be thought of as this two-step process where you first sample from some simple distribution U, which is usually uniform, some random numbers that you sample, and then you apply some nonlinear mapping, G theta, which depends upon your parameters, and then you get data from your model. I mean, that's basically any generative process can be defined like that, right? All right. Now, ideally, what you would do is, given that you have a likelihood function, P of x given theta, you would do maximum likelihood estimation, which is this, or if you're Bayesian, you would sample from your posterior given your likelihood and your prior. But all of these methods, the standard statistical estimation techniques, they require access to the likelihood function, which you may not have in for many models. The model that I gave the example of is exactly one such model where you do not have a tractable likelihood function, which means that you cannot evaluate it given different parameter values, which means that you cannot do your MCMC sampling or your maximization of the likelihood. So this causes of intractability of the likelihood function can be multiple. Your model can just be a simulator, which is like a computer program, which is like, okay, input this, do this, then solve this, and blah, blah, blah. And then there's multiple steps. And in the end, what you get is something which you cannot even maybe write down the likelihood function of because it's just too complicated process. Or there are variables that are important for model description that are unobserved, which is exactly what happened in our previous example that I showed. Here, if you had observed your betas and your taus, then it's basically just a Gaussian likelihood, and then your tau comes from a Poisson point process, which also has a normal likelihood. But the thing is, you don't observe these taus and betas. What you observe is this kind of a red signal, right, which is kind of a superposition of all of these. And so since you don't know it, it's difficult to evaluate or write down the likelihood function. Anyway, so what do people... So the first thing is, such kind of models is not very specific to this radio communication example that I gave. It occurs, in many scientific science and engineering fields like population genetics, where it all started, so to speak, ecology, astrophysics, epidemiology, and so on and so forth. Because, I mean, the models are getting more and more complicated because, your computers are getting more and more, the performance of the computers are increasing. So you don't really need to have, you're not limited by computation, right? So you can have very, very complicated real world models. And so in order to fit these models, what you do is what is called simulation-based inference or likelihood-free inference, because of course, we don't have likelihood. So we want to do something likelihood-free. And so the rest of the talk is basically me telling you about simulation-based inference, and in particular, this the most common way of doing simulation-based inference, which is called approximate Bayesian computation. So you're not fully Bayesian, you're going to be approximately Bayesian. And then I'll tell you how we solve the problem that I showed in the first few slides, which is this radio propagation model. And then we'll get into some of the details of and the problems in existing simulation-based inference methods. Okay, so approximate Bayesian computation is a simulation-based inference or likelihood-free inference method that permits sampling from the approximate posterior of any generative model. And so the very basic rejection ABC algorithm is something like this. You sample a prior, from your prior P of theta, you sample some parameter value. Using that, you simulate from your model, some Y. And then you compute the distance between your simulated data and the observed data that you have collected in real world. And if that distance is small enough, which is given by this epsilon, then you accept that theta star to be from this approximate posterior that you're after. And then you keep on repeating that process till you get n number of accepts. And then that forms a sample from your approximate posterior, which can be written like this. So instead of p theta given x, what you have is p theta given this condition. And then here is D is a distance or discrepancy metric. That's what's important here, because now we're not relying on the likelihood. We are relying on sampling from your model and then computing some sort of a distance between data sets. Epsilon is also what is needed here, as you can see, because, but this is not that much of a problem in practice, because you can compute distances for different data sets and then just select the ones that give you the the least number of least distances. One thing which is implicit here is that you also need some sort of a mapping or a embedding of your data set if your data set is very high dimensional. Usually, if let's say your simulator is of images or the time series data that I showed you, it's like 800 dimensions. Computing distances in high dimensions is not a very good idea. So people usually try to compute some statistics of your data sets and then just compare those statistics. All right, and then the approximation here lies because we are not, we have this kind of tolerance threshold. If this threshold goes to 0, then we converge to the true Bayesian posterior. But of course, if your Y, the data is continuous domain, then you'll never get a 0 distance. So yeah, there's always this approximation there. Okay, so to sum up, these are the discrepancy-based, simulation-based inference methods. There's two. The ABC is what I showed you just now. And then there's also minimum distance estimation, which is like a frequentist version of that. So instead of sampling from this posterior, you just minimize some distance between your model and your data set that you have gotten. Okay. Now, I just would like to say that this is how any inference actually works. Normal inference also works in exactly the same way as this. You just take the distance d to be KL divergence. Then you get, in the end, what you get is you maximize the likelihood, right? Or minimize the negative log likelihood. But in this case, the point is that KL divergence is not a good metric because we cannot compute it because it relies on the likelihood function. So the idea is then to pick a different distance, which maybe we can compute from samples, right? And the more accurately we can estimate this distance with fewer data points, that is going to help us in doing either of these two methods, right? So this D, you need to estimate with only samples from your model, which is P theta. And I mean, QN is basically already just your data set. So it should be, so you're basically estimating this data set with this distance with samples. And if you can estimate in few samples, then you don't need that many, simulations from your model. All right. And this is, so this is exactly what I was trying to tell you, that you have a distance which you approximate using only, let's say, m samples from your model, and n samples is your observed data set size. And what you want is a distance which is kind of efficient, so that it does not require a large number of m to estimate, this distance. And this is what is we term sample complexity, which is how quickly your error, which is the difference between this and this, goes down as a function of m. And so now there are many discrepancies in the likelihood-free inference literature as well. There is a sample-based version of KL divergence. There's Wasserstein distance and other optimal transport metrics. And then there's also what is called maximum mean discrepancy. And this is highlighted because that's what I'll be talking about the most. So now maximum mean discrepancy is a nice distance to be used here because it's efficient. It's more efficient than all of the others, and efficiency in terms of sample complexity, as we'll see later on. And it has been it leads to very nice estimators with nice robustness properties. And it can be defined for basically any data set for which you can define a kernel. So these are the only kind of requirements that it has. And so it's kind of flexible in that sense. And so to solve this initial problem, the radio propagation problem that I showed before, that model, we are going to take the distance to be this maximum mean discrepancy. All right. And so a little bit more introduction on what maximum mean discrepancy is. So let's say you have two distributions, P and Q, which you want to compare the distance between. Okay, and that's what we are doing here. And MMD is kind of one notion of such a distance. What it does is, let's say you have this red is the density of the distribution P, and then blue is the density of this distribution Q. What it does is, using some sort of a kernel function, it maps these distributions as to a point in some function space. Okay, and then MMD is just the distance between these 2 points in the function space, and which can be thought of as comparing infinitely many moments, because let's say this function space only has one function in it, which is the mean. Okay, so then in this equation, basically, you remove k and just put an x. So all you're doing is you're comparing the mean of two distributions. And then, but of course, the distributions can differ in other ways, even if their means are the same, right? So in order to be able to, have a distance which is non-zero for two non-identical distributions, you need to pick the kernel slightly appropriately. So that means that this function space should not just have one or two functions, but it should have many, many functions, so that you can compare, infinitely many moments of, the two distributions. Anyway, and so the standard choices of kernel, like a squared exponential kernel or a Gaussian kernel or Matern kernel, these are all good choices, which lead to, the distance between P and Q being 0 only if P equals to Q, which is the property that we would need. Okay, so that's basically MMD. Again, the good thing is that the squared of the MMD can be written as these double expectations, some of these double expectations. So these expectations are with respect to P and Q. The good thing is that you can estimate it very efficiently with samples by replacing all of these expectations with their Monte Carlo estimate. So each integral you replace by its Monte Carlo estimate, and all you need to do is you need to evaluate this kernel function, and that's it. You don't need to go to any infinitely dimensional feature space. You just define a kernel function, evaluate given your data set, and then do this kind of a sum, and that's it. You get an estimate, which is a minimum variance estimator for this MMD squared. All right. Now, then the choice of kernel is now important here, right? We've already picked a distance, but in order for it to be applicable to our method, we need to pick a kernel appropriately. And so this, of course, comes from your domain knowledge, depending upon the kind of data you have, the kind of model you have, and so on. And so for our case, we have these kind of time series models, right? And so we define some sort of a kernel here, which relies, you don't have to look into this slide too much, but the point is that we take those time series that I showed you earlier, and then we compute some, let's say, embeddings of it, which are called temporal moments. And then we place a kernel on these embeddings instead of, this 800-dimensional time series. Okay, once we do that, then we are able to fit different models to it. This red one is the kind of model that I gave an example earlier. In black, what you see is the data. And then in blue is another model, which is not this, point process-based model, but it's a different model. The point is that we are able to fit both of these models to this data without having, access to the likelihood function, without, needing to do any domain-specific stuff, which is what people do in that field. All right, but as you can see, what's happening here is the red one doesn't look exactly as the black one, right? The blue one looks very much similar. It kind of models this initial, peaks, but the red one only models, let's say, the slope of this decay and so on. And that is because our model is essentially misspecified. If we have time, we'll get into that later. But the point is that the model, the data has certain characteristics. And the model cannot produce such kind of looking data no matter what parameter value you pick. Okay, which means that your data distribution is kind of outside your model family. This is how we define the model misspecification. Anyway, this, if we get time, we'll come back to it later. Okay, so that's how we did solve that problem. Now, there were two practical issues in simulation-based inference. So the one is, as you saw, that we always rely on simulations from the model, right? We need to do, let's say, this rejection sampling type of method. That means you need to keep on simulating from the model and keep on, plugging in different parameter values and then getting synthetic data out of it. Now, if your model is computationally costly, then you are kind of limited in terms of how much compute you have, right? So you cannot have thousands and thousands of data points. So you need to do something more sample efficient in that case. The other problem is what I just alluded to, is that if your model is misspecified, then you can run into those problems as we just saw. And you might get inference results which don't even make sense. Okay, so now we'll look at each of these problems one by one. I'll start first with what do you do when the model is computationally expensive to evaluate. A recap of the problem setup again. You have some data, you have a model family, you need to estimate theta given data. And now simulating this data from your model is costly, which means that when you apply this step, y equals to this g function of these random numbers, that is going to take time. Maybe you're solving some differential equations there, or some other physics equations. That takes time to generate even one data point. And so for that, you need methods that are able to perform inference with fewer samples, which brings us to a sample efficient simulation based inference method that I'll talk about now. All right, so let's go back to this maximum mean discrepancy, because that's the distance metric that we picked, right? And as I was saying, that when you replace all of these expectations with its Monte Carlo estimate, the sample complexity rate that you get is 1 over square root of m, which is basically your Monte Carlo error rate, right? So how quickly your Monte Carlo estimate approaches the true quantity as a function of the number of ID samples that you take. All right. Now, this is already very good, I would say, at least compared to Wasserstein distances and Sinkhorn divergences and other alternatives. Sorry, went a bit far. All right. So it's already good, but to reduce error by half, you still need 4 times the number of samples, right? It's 1 over square root of m. And so then we looked at how can we kind of improve the sample complexity of MMD estimators. Note that here n is the number of data samples. That does not change because that's just the data that you have gotten. So I'm going to drop n 1 over square root of n from everywhere. And so we'll only focus on how many samples we need from the model, because that is what is in our control. All right, so instead of this Monte Carlo estimator that we just saw, what we do in this paper is we propose an optimally weighted estimator of maximum mean discrepancy, where instead of 1 over m that was in your previous slide, I just replace that with a weight w. So that means each ID sample that I have, I'm going to weight it slightly differently. And hopefully by weighting it differently, I'll be able to estimate the MMD much more efficiently, accurately. And so this is kind of the pictorial representation of what's happening. You go from your data space X to this function space. And so your data points are mapped into this kernel mean embedding. So there's a point in the function space. And so let's say this is your true point, which you would get if you could evaluate all the integrals in closed form. But if you estimate, you get here. But we are saying that, okay, maybe if we can weight the points differently, we'll be able to get closer to the truth. All right, now we'll derive these weights and in what sense they are optimal. So now let's say your model can be estimated by like this empirical distribution of y, and now it's not 1 over m, but now it's differently weighted samples. First thing what we do is, if you see the left hand side of this inequality, that's just the true MMD between your model and some data generating process, minus the MMD with only m samples, right? So that's basically your error that you get by going from the true model to only m samples from the model. Now, this can be upper bounded by this quantity, which is basically p theta and this one. How this is basically just a reverse triangle inequality. So it's just saying the distance between A and B minus distance between B and C is less than equal to distance between A and C, right? Usually you would have seen the triangle inequality. It's just make a, reverse this integral, put a minus, and then you'll get the reverse triangle inequality. All right. The good thing about this is now we removed Q, which we don't know. That's the true data generating process, which we don't have access to. So all we need to do is minimize this guy with respect to W. That will give us, a W which is optimal in that sense, right? Okay, now let's assume that you have another kernel C, which is on the space of these random numbers that you need for your model. Okay, so K was the kernel on the space of your data, which is like this 800 dimensional time series, for example. And then C is just a kernel on the space of how many random numbers do you need, to generate one data point. That is a kernel that we pick. And assuming that, under the condition that the composition of K and your generating function lies in the function space of this C, we can show that this quantity, which is our quantity of interest, can be upper bounded by this quantity. The good thing here is now we go from something which is an MMD on K to something which is MMD with respect to the kernel C. And this is the MMD between this distribution U, which is the distribution with which you sample your random numbers. And this is typically uniform or Gaussian, right? Because even if you need gamma or Poisson or whatever, you can map everything back to a uniform distribution, because all the random numbers are generated by using this inverse probability theorem, whatever it's called, log CDF, something. Anyway, so now what we do is we pick a W that minimizes this quantity over here. The good thing is that since it's with respect to this simple distribution, I can compute this MMD, these expectations that we showed earlier in closed form. Okay, and the argument that minimizes this will be the one that minimizes the square of this. And so in the end, what I have is a squared objective. I can differentiate it, put it to 0, and then I get my W star in closed form. Only because now this U is a Gaussian or a uniform, and so I can compute the integrals of any kernel with respect to that. Okay, to sum up, we wanted to minimize W with respect to this quantity, right, which is our error. So that will give you an error, a weight which has minimum error. We first upper bounded using this quantity. Then under some condition, we show that this quantity is actually upper bounded by this quantity. And then we minimize this quantity. And now hopefully the gap between this quantity and the MMD with respect to C is not that much. What's essentially happening is you're approximating a function space that corresponds to the kernel K with another function space which corresponds to kernel C. And so if you pick C appropriately given K, you can actually approximate such functions. For instance, if K is very non-smooth functions, okay, and you pick C, which is absolutely infinitely smooth, which is like a Gaussian kernel, then you cannot approximate non-smooth functions with combinations of smooth functions, right? But the other way around you can do. And so that is kind of how we tell to select C, that it should be as smooth as possible, but not smoother than the kernel that you have picked on your data set, such that this gap between the two function space gets minimized, and then your method would work better, right? Because then upper bound is tighter. All right. Now, what is our sample complexity result? Because it was 1 over square root of m for the Monte Carlo sampler, and what we get is a quantity that looks like this. Now, nu C is the smoothness of this kernel C that I was talking about. So that means that it should be as smooth as possible, because then our rate increases, right? But it's also divided by this S, which is the dimension of the number, the random numbers that you need. So for one data point, how many random numbers do you need? That's basically S. And so your as the dimension of these random numbers increase depending upon your model, the gains that you get, the rate is going to slow down. If you pick a C, the kernel C, very smooth, then your rate is going to be up. The good thing is that no matter what new C and S you pick, it's still better than 1 over square root of M, the rate, because it gets added here. So no matter S, I mean, when S goes to infinity or when new C goes to 0, you get back the rate of your Monte Carlo estimator. All right, and as I was saying, then the choice of C kernel depends upon how smooth your kernel K is. And, from a computational viewpoint, then you can pick K very smooth. And yeah, that's basically it. So that's the method and the result of the sample complexity. Now, how many minutes do we have?
Basically 5 minutes, but I mean,
it's fine.
We can restart it late.
Okay.
Yeah.
No problem. Okay, so these are the two things first, I guess we can see, or maybe we can skip. So here I'm changing the kernel K and C and then seeing which one has a lower error. And you can see that the lowest one is when C is Merton, which means that it's not very smooth, but K is very, very smooth. So that's the condition that I talked about. That's when you get the lowest error. When it's the opposite, that means your kernel C is very, very smooth and you're approximating functions which are not very smooth, then you are not as good, basically. Anyway, so what's the point of this method? Let's say now you're a wind farm engineer and you have these models of large scale offshore wind farms, and you want to compute, how do I, let's say, the efficiency of your wind farm. And so your parameter in this case is the angle with which the wind is blowing. And so it's just one parameter, very simple. But then to simulate from this model, it takes like roughly 2 minutes for one data point, which already is way computationally expensive for all these simulation-based inference methods that we talked about. And so to generate 1,000 data points with m equals to 10, it took around 245 hours. And so when we do ABC with our method, so using MMD, which is our optimally weighted one, versus the normal V statistic estimator, you can see that with the same amount of data set, we get slightly more concentrated posterior, which is, let's say, slightly more accurate result. Or in other words, you can say that we could have stopped simulating many hours before and still gotten the same amount of results. So that's kind of the gain, that the computational gain that you get. To be honest, I can actually stop here because I think that's already enough, and I'm sure people have things to go to. What we didn't get into is how do you handle this when the model is misspecified, which is when your family of distributions that you have defined, which is your model, is incorrect. And this can happen due to outliers in the data, because the way you collected the data, there might be broken sensors, which leads to missing data. There might be broken independence assumptions. All of these cases which can contribute to your model being misspecified, or the fact that all models are approximations of real world, so you're never going to capture everything. All of these cases means that your model becomes misspecified, which is a problem for any inference, Bayesian or frequentist, but even more so for simulation-based inference, because now you're literally relying on simulations from the model to do inference. That means you're relying on the wrong model to simulate and then compute distances or do whatever. And yeah, so basically the rest of this talk would have been how we address that. But if you are interested, you can basically look at this paper from last year. And yeah, that's it. I would rather have some questions and not overload with the rest of the talk. So thank you.
Do you have questions?
I guess that's
Yeah, it's I'm so sorry.
No, it's fine, it's fine.
I feel like both problems are so interesting and important. So
But from a practical viewpoint, I think, I mean, overloading of information also doesn't help anyway. I could go on longer and longer, but it's not going to, the amount of information you gain has already saturated now. So
that's true.
anyway, so what I would like to end up with, since nobody's asking any question, if I can get to the last slide, is basically take home messages. And the only thing that I want you to remember is that there are models with intractable likelihoods in many domains of science and engineering, and that simulation-based inference are actually tools for handling such cases. And that there's basically just two, well, not just two problems, there are many problems, but the two problems that I'm interested in and which I think are very practical issues that arise is when your model is expensive, and then you're limited with the amount of data that you can have, and when your model is wrong, but you still want to fit it, right? Because it tells you something about the problem that you're tackling. And so, yeah, that's pretty much it. Yeah. Thank you. Thank you for listening.